Alien worlds exist where rivers of molten rock flow beneath twin suns. The cosmos holds over 5,000 known exoplanets, and 30 stand apart as the most likely places to find life. By the end of this journey, you will know which of these distant worlds could be home to another civilization. We will explore planets locked in eternal daylight and vast water worlds with global oceans. How many of these 30 worlds do you think could truly harbor life? Our journey begins just 4.2 light years away, a cosmic stone's throw in the vastness of space. Orbiting the star Proxima Centauri is a world named Proxima Centauri b. It is our closest known exoplanet, a neighbor in the grand scheme of the galaxy, and it holds a tantalizing secret. This world has a mass remarkably similar to Earth's, suggesting it could be a rocky planet just like our own. Even more exciting, it resides within what astronomers call the habitable zone, that special region around a star where temperatures might be just right for liquid water to exist on the surface. Picture vast, dark oceans under a dim, crimson sun, yet this potential paradise faces a brutal reality. Its sun is a red dwarf, a type of star known for its violent temper. Proxima Centauri frequently unleashes devastating flares, eruptions of radiation and charged particles, hundreds of times more powerful than anything our sun produces. These stellar tantrums could strip away a planet's atmosphere and bathe its surface in deadly radiation, scorching any chance for life as we know it. So the great mystery of Proxima b is a stark contradiction. Is it a water-rich world huddled close to its faint star, perhaps harboring life in deep oceans or underground? Or is it a barren, irradiated rock, a testament to the harsh conditions so common in our universe? This duality is what makes it a prime candidate, a world of profound possibility and peril, sitting right on our cosmic doorstep. But this world's challenges run even deeper than its stellar flares. Proxima Centauri b is almost certainly tidally locked to its star. This means the same hemisphere constantly faces the sun, locked in an eternal gravitational embrace. One side of the planet is a land of perpetual, searing daylight, while the other is plunged into an endless, frozen night. You might think such a world offers no middle ground, yet the most fascinating region could be the narrow ribbon between these two extremes, a place astronomers call the Terminator line. Here, along the permanent boundary of dawn and dusk, conditions might be just stable enough for liquid water to persist. Imagine a world without sunrise or sunset, where the sun hangs motionless on the horizon, casting long, permanent shadows. Life here would face an environment unlike any on Earth. Hardy organisms might cling to existence in this twilight belt, drawing energy not from a moving sun, but from the constant, gentle glow along the horizon. Perhaps photosynthetic life would learn to thrive in the dim, red light, or maybe ecosystems would rely entirely on chemical energy from volcanic vents. This Terminator line represents a fragile, hopeful zone, a potential oasis squeezed between a scorching desert and an icy wasteland. Could entire civilizations evolve in a narrow, ring-shaped world, forever walking the line between day and night? The possibility forces us to expand our very definition of what a habitable world can be. Just 40 light years away, an entire solar system exists around a star so faint you could not see it with your naked eye. This is the TRAPPIST-1 system, and one of its 7 known worlds, TRAPPIST-1e, stands out as a top contender for life. It is a rocky planet, very similar to Earth in both size and mass, and it sits perfectly within its star's habitable zone. Think of a world with a potential for Earth-like temperatures, where water could flow as freely as it does in our own rivers and lakes, but the true wonder of TRAPPIST-1e comes from its family. All 7 planets orbit incredibly close to their dim red dwarf star and to each other. the entire system would fit easily within the orbit of Mercury around our Sun. This proximity creates a celestial dance unlike anything we know. If you were standing on the surface of TRAPPIST-1e, the other worlds would dominate the sky, appearing as large as our own moon or even bigger. You would see their geological features in stunning detail, watching as these neighboring worlds glide past one another in a silent, perpetual ballet. This closeness raises a thrilling possibility. Could these planets share the ingredients for life? Some scientists speculate that if an asteroid struck one world, it could blast pieces of rock containing microscopic life into space. These fragments could then travel the short distance to a neighboring planet, seeding life across the entire system. Alternatively, they might even share parts of their atmospheres, creating an interconnected network of worlds. TRAPPIST-1e is not a solitary oasis, but a member of a planetary archipelago, offering not just one, but multiple chances for life to arise and flourish. The concept of a planetary family is extraordinary, but what about a world that stands alone as a cosmic twin? Over 500 light-years from Earth, the Kepler Space Telescope found an answer. Kepler-186f was the first validated Earth-sized planet ever discovered orbiting within the habitable zone of another star. This was not just another exoplanet, it was a milestone. For the first time, humanity could point to a distant sun and say with confidence that a world with a similar size to our own exists in that region where liquid water is possible. It orbits a red dwarf star, much like the stars in the TRAPPIST-1 system, but its discovery changed the entire conversation. Before Kepler-186f, we knew of larger planets, often called super-Earths, in habitable zones. But finding a world so similar in stature to our own confirmed a profound idea. Earth-sized worlds in the Goldilocks zone are not rare, fluke occurrences. They are common throughout the Milky Way. The galaxy is likely filled with billions of planets that share this basic, life-friendly characteristic. Imagine the view from its surface. The star would appear much larger in its sky than our Sun, glowing with a dim, orange-red light. A year on this world passes in just 130 Earth days. The plants, if any exist, might have evolved to absorb the specific red wavelengths of light from their sun, painting the landscape in hues of black and deep purple. The existence of Kepler-186f is a powerful testament to the sheer number of opportunities for life out there. It transformed our search from a question of if such worlds exist to a question of how many we will ultimately find. Yet another red dwarf system holds a world that fundamentally reshapes our search. LHS 1140b is a super-Earth, a planet significantly larger and more massive than our own, and it presents an almost perfect laboratory for the next phase of our quest. What makes this world so compelling is not just its location in the habitable zone, but the character of its star. Unlike the flare-prone Proxima Centauri, this red dwarf is remarkably calm and quiet. It offers a stable, gentle light, providing a far more forgiving environment where an atmosphere could potentially survive and thrive for billions of years. This stability is the key that unlocks an incredible opportunity. LHS 1140b is one of the very best targets for the James Webb Space Telescope. As this giant world passes in front of its star, Webb can analyze the starlight filtering through its atmosphere. It will search for the chemical fingerprints of key molecules, the biosignatures that could hint at life. The telescope could detect the telltale signs of water vapor, methane, or even oxygen, a gas on Earth that is overwhelmingly produced by living organisms. Imagine the possibility of looking at the air of another world and finding it rich with the same kind of gases that blanket our own planet. Is LHS 1140b a vast, water-covered world, a global ocean glistening under a red sun, or is it a rocky supercontinent with climates we can scarcely imagine? The quiet nature of its star gives this world a precious chance to hold on to its secrets, and soon we may be able to read them in the light. Ross 128b offers a different kind of promise, a world sheltered by a remarkably gentle sun. Just 11 light-years away, it is one of our closest planetary neighbors, orbiting a red dwarf that is conspicuously quiet. Unlike the violent tantrums of Proxima Centauri, this star emits very few flares, bathing its planet in a stable, consistent light. This calmness is a critical advantage for the potential development of life. Without the constant barrage of sterilizing radiation, Ross 128b stands a far better chance of holding onto a thick, protective atmosphere. Think of the difference between living under a temperamental volcano and in a serene, sunlit valley. This stable environment allows complex chemistry to proceed uninterrupted for eons, potentially giving life the time it needs to emerge and evolve. The planet itself is classified as a super-Earth, larger and more massive than our own world, which could help it maintain a strong magnetic field to further shield its surface. What kind of world might it be under that steady crimson glow? It could be a rocky landscape with vast, tranquil seas, or perhaps a world with a dense, nitrogen-rich atmosphere similar to our own. Its stability makes it a prime target for the next generation of telescopes, which will scan its skies for the chemical signs of a living world. Ross 128b represents a quiet hope, a world where the conditions for life are not just possible, but peacefully persistent. Deep within the constellation Aries, a star so faint it was only discovered in 2003 holds a profound secret. Teegarden star is an ancient red dwarf, a stellar senior citizen that has burned for billions of years longer than our own sun. Orbiting this quiet old star is Teegarden star B, a world with a mass almost identical to Earth's, nestled perfectly within the habitable zone. Its star's remarkable stability is its greatest gift. While younger red dwarfs are known for their fiery outbursts, this one has long since settled into a gentle, predictable rhythm. This offers the possibility of a truly temperate climate, a world where temperatures could be surprisingly Earth-like, free from the violent stellar storms that plague other systems. But the most staggering implication is time itself. This planetary system is ancient. It has existed for roughly twice as long as our own solar system. Just think of the immense span of time that has been available here. On Earth, life arose relatively quickly, but it took over 4 billion years for complex, intelligent life to emerge. Teegarden star B has had double that time. What could possibly have evolved on a world with 8 billion or even 10 billion years of uninterrupted, peaceful development? Life there could be vastly older, more complex, and more advanced than anything we can conceive. It might have evolved into forms of intelligence that have mastered their world, their star, and perhaps even the fabric of space itself. This planet does not just ask if life could exist, it dares us to wonder what life becomes when it is given almost all the time in the universe. Far from the turbulent red dwarfs lies a different kind of star, and a world that may be one of our most promising twins. Kepler-442b is an exoplanet that ranks among the most Earth-like worlds ever found. Astronomers measure this similarity with something called the Earth Similarity Index, and Kepler-442b scores remarkably high. It is a rocky world, only slightly larger than our own, and it orbits comfortably within the habitable zone of its sun. But the true secret to its potential lies not just in the planet, but in the star it calls home. This star is a K-type, often called an orange dwarf. It is a gentler, more stable star than the volatile red M dwarfs we have encountered so far. Orange dwarfs burn brighter and warmer, they are far less prone to violent flares, and they have incredibly long, stable lifespans. Imagine a sun that shines with a warm, golden light, offering a more familiar day and night cycle to any potential life on the surface. The planet's orbit takes about 112 Earth days, meaning its years pass in a gentle, steady rhythm. This combination of factors creates a world that might not just be habitable, but genuinely comfortable, with more consistent stellar energy and a lower threat of radiation storms. Kepler-442b could maintain a temperate climate and a thick atmosphere for billions of years. This stability provides an enormous window for the complex chemistry of life to begin and to evolve. While it is more distant than our other candidates, its profile makes it a tantalizing blueprint for a second Earth, a world where the conditions for life are not just a precarious possibility, but a long-term promise. Another super-Earth, GJ 357d, hides within a system just 31 light-years from our own. This world is substantially more massive than our planet, a heavyweight contender in the cosmic arena for life. It resides squarely within its star's habitable zone, but its true nature remains one of the great puzzles of exoplanet science. Is it a vast, rocky landscape, a supercontinent scaled to its enormous size, or is it something even more alien? Computer modeling paints two very different portraits. One suggests a terrestrial world, a scaled-up version of Earth with a robust atmosphere and familiar geology. The other, more tantalizing possibility is that GJ 357d is a water world, a globe completely enveloped by a deep, global ocean hundreds of miles deep. Picture a planet with no land at all, only a single, endless sea stretching from pole to pole under the light of its dim red sun. The immense pressure at the bottom of such an ocean would create exotic forms of ice, not cold, but hot and dense, forming a solid floor to the aquatic abyss. Could life swim in those dark, pressurized waters, far from any starlight? The key to unlocking this mystery lies in its air. Astronomers are now focusing their most powerful instruments on this world, attempting to catch it as it transits or passes in front of its star. If it does, the James Webb Space Telescope could analyze the starlight filtering through its atmosphere, searching for the spectral signatures of water vapor, oxygen, or methane. Detecting an atmosphere at all would be a monumental step, confirming that this massive world can hold onto a protective blanket of gas. The quest for GJ 357d is a race to define its very essence, to determine if it is a waterlogged globe or a colossal terrestrial planet, and in doing so, to see if it belongs on the short list of worlds that could truly cradle life. Sometimes the most profound discoveries are not made in the telescope's first glance, but in a second look at the data. Kepler-1649c was one such hidden treasure, an Earth-sized world that had been missed by computer algorithms and was only found years later by a team of diligent human eyes scanning old Kepler mission archives. What they uncovered was arguably the most Earth-like exoplanet we have ever found in terms of both size and temperature. This rocky world orbits squarely within its red dwarf star's habitable zone, and it receives about 75% of the starlight that Earth gets from our sun. Picture a world where the sunlight is a perpetual, gentle twilight, a soft crimson glow that might feel similar to a late afternoon on Earth. The potential surface temperature could be remarkably similar to our own planet's, raising the incredible possibility of liquid water oceans and Earth-like weather patterns. This combination of familiar size and familiar heating makes it an exceptional candidate, a world that feels less like an alien environment and more like a cousin to our own. How would life adapt to a sky dominated by a dim red sun? Plants might evolve to absorb every possible photon, their leaves appearing deep black to our eyes to capture the full spectrum of available light. The discovery of Kepler-1649c is a humbling reminder that our greatest finds might still be hiding in plain sight. waiting for a curious mind to notice them. It stands as a beacon of hope, a world that so closely mirrors our own basic conditions that it fuels the belief we are not just looking for life, but for a place we might one day recognize as home. The search for a second Earth often focuses on rocky worlds, but a truly alien ocean may be hiding in plain sight. K2-18b is a different kind of candidate, a world that defies our simple categories. It is classified as a mini Neptune or a super-Earth, a planet significantly larger than our own, but smaller than the ice giants in our solar system. For years, scientists assumed such worlds were gaseous, with crushing pressures and no solid surface, utterly hostile to life. Then came a discovery that shattered that assumption. When astronomers pointed the Hubble Space Telescope at K2-18b, they detected the unmistakable signature of water vapor in its atmosphere. This was not just another detection, it was a revolution. It was the first time water vapor had been found in the atmosphere of a planet within the habitable zone of its star. This single finding opened up an entirely new class of potentially habitable worlds, planets now known as Hycean worlds. The term Hycean blends the words hydrogen and ocean, and it describes a planet with a vast, hydrogen-rich atmosphere enveloping a global, planet-wide sea. Imagine a world with no continents, no islands, just an endless, dark ocean stretching in every direction. The sky above would not be blue, but a thick, hazy envelope of hydrogen, and the ocean below could be dozens or even hundreds of miles deep. The pressure at the bottom would be immense, creating a strange barrier where liquid water meets a hot, dense layer of ice. This is not an ocean as we know it, but a global abyss. The debate now centers on whether life could exist in such an alien environment. Could biological processes thrive in a sea under a hydrogen sky, completely cut off from the rocky seabed we typically associate with life's origins? The answer might be yes. On Earth, we find extremophiles thriving in the most hostile conditions, from deep sea vents to toxic lakes. A Hycean world could offer a vast, temperate liquid water environment, a stable globe-spanning habitat where life could originate and evolve in its deep, dark waters. The detection of water vapor on K2-18b did more than just identify a promising world. It forced us to broaden our imagination and accept that the most likely homes for alien life might be nothing like Earth at all. The very air of K2-18b whispers of a new kind of paradise. This Hycean world presents a radical alternative to the search for a second Earth, a place where life could flourish without a single grain of soil. The core idea is both simple and profound, a planet dominated by a massive, global ocean trapped beneath a thick, hydrogen-rich atmosphere. On such a world, the concept of land is alien. There are no mountains breaking the surface, no continents to divide the seas, only an endless, dark water world stretching from pole to pole. The ocean itself could be hundreds of miles deep, a volume of liquid water that makes all of Earth's seas combined seem like a puddle. At the very bottom, the pressure would be so immense that it would forge a strange barrier, a layer of solid ice that is not cold, but hot, heated by the planet's internal warmth and the crushing weight of the ocean above. This is not the familiar ice of our winters, but an exotic, high-pressure form of water that acts as a solid floor to the abyss. Could life exist in such a place, completely adrift in a global sea? The possibility is startlingly real. On our own planet, we find entire ecosystems thriving in the deep, dark ocean, far from any sunlight, sustained by chemical energy from hydrothermal vents. A Hycean world could offer this on a planetary scale, a stable, globe-spanning habitat where microbial life could originate around similar vents on the ocean floor. But what about more complex creatures? The sheer scale of this environment provides an almost unimaginable amount of living space. Evolution, given enough time, could fill that dark water with life forms we can barely dream of, organisms adapted to navigate a world of perpetual twilight under a hazy, orange sky. They might sense their world through sound or pressure changes, communicating in ways we have yet to discover. The most exciting clue, however, lies in that hydrogen atmosphere itself. Hydrogen is a simple gas, and when a planet transits its star, starlight filters through this air more easily than through a thick, complex atmosphere like our own. This transparency makes it far simpler for our telescopes to detect the chemical fingerprints of potential life. Scientists could search for gases like dimethyl sulfide, a compound on Earth produced by marine phytoplankton, or other biomarkers that would be clear signs of biological activity. Finding such a signature in the air of a Hycean world would not just tell us that life is possible there, it would reveal an entire new blueprint for a living planet, proving that the universe's recipe for life does not require an Earth-like kitchen. The steady glow of a quiet star offers a different kind of promise. Orbiting the M-dwarf star TOI 700, just over 100 light-years away, is a world that checks nearly every box for potential habitability. TOI 700d is an Earth-sized planet, a rocky world almost identical in size to our own, and it sits perfectly within its star's conservative habitable zone. This world was discovered by NASA's TESS mission, a planet hunter designed to find worlds around our Sun's closest neighbors, but what truly sets this system apart is the star itself. Unlike the flare-prone red dwarfs we have encountered, TOI 700 is exceptionally calm and stable. It has shown no signs of violent outbursts, bathing its planets in a consistent, gentle light for eons. This stability is a gift, allowing for the possibility of a planet that has held onto its atmosphere and developed a temperate climate. Scientists have run sophisticated computer models to envision what kind of world TOI 700d could be, and the results are fascinating. One compelling scenario suggests it could be a water world, a globe completely shrouded by a deep, global ocean with a dense, cloud-filled atmosphere. Another model paints it as a more familiar landscape, a world with significant landmasses and bodies of liquid water, much like a scaled-up version of Earth. In either case, the potential for surface liquid water is strong. The planet is also tidally locked, with one side in perpetual daylight and the other in endless night, but climate simulations indicate that a thick atmosphere could efficiently distribute heat around the entire globe, preventing the day side from scorching and the night side from freezing solid. This could create a vast, temperate region along the Terminator line, or perhaps even make the entire planet a haven for life. With its ideal size, its prime location, and its peaceful sun, TOI 700d has become one of the highest priority targets for the James Webb Space Telescope. The next step is to point our most powerful instruments toward this silent star and finally analyze the air of this tantalizingly Earth-like world. The cosmic neighborhood of GJ 667cc is anything but ordinary. This super-Earth does not orbit a solitary star, but is part of a complex triple star system, a celestial dance of three suns sharing the same gravitational space. The planet itself is tethered to the smallest of the three, a faint red dwarf, and sits squarely within its habitable zone. From the surface of this world, the primary sun would glow a deep red in the sky, but the other two stars would also be visible, appearing as incredibly bright, piercingly white points of light, casting faint secondary shadows and illuminating the landscape even during the night. You would experience a sky with multiple sunsets and sunrises, a perpetual ballet of light. The presence of multiple stars might seem like a chaotic influence, but in this specific configuration, it creates a surprisingly stable environment. The other two stars orbit much farther out, acting as distant companions rather than disruptive forces. This stability is the key to the planet's potential. GJ-667c is a massive world, a super-Earth with more than 4 times the mass of our own planet. This greater gravity could help it hold onto a thick, dense atmosphere, one that would efficiently trap heat and distribute it around the globe. This is crucial because the planet receives slightly less light from its dim red sun than Earth does from ours. A robust atmosphere would act as a planetary blanket, preventing the world from freezing over and instead creating a potentially temperate, if somewhat dark, environment. The sheer longevity of such a system offers a profound promise. With multiple stars gravitationally bound, this cosmic arrangement could remain stable for tens of billions of years, offering an almost unimaginable timescale for life to not only begin but to evolve into forms of incredible complexity. This world is a testament to the idea that stability can be found even in the most seemingly chaotic corners of the galaxy. While many promising worlds orbit fiery red dwarfs, a different kind of hope shines from a star much more like our own. Kepler-442b circles a G-type star, a virtual twin to our Sun, earning it the nickname Earth's cousin. This world is not just similar to Earth in its stellar environment, it is also about 60% larger in diameter, placing it in the category of a super-Earth. Its orbit within the habitable zone feels deeply familiar, taking 385 Earth days to complete a single year. Imagine a calendar and a seasonal cycle almost identical to our own, but on a planet with a stronger gravitational pull and potentially vast, sprawling continents. Under the warm, yellow light of its sun-like star, the conditions for an Earth-like biosphere seem incredibly plausible. Rivers could carve canyons through ancient landscapes, and oceans might host tides under the gaze of moons we have yet to detect. The potential for photosynthesis is strong, suggesting that any life there could bask in sunlight very similar to our own, yet this cosmic mirror holds a glimpse into a distant future. The star Kepler-442 is older than our Sun by over 1.5 billion years. This advanced age means the star is gradually growing brighter and hotter, slowly pushing the inner boundary of the habitable zone outward. For now, Kepler-442b enjoys a prime position, but in the coming hundreds of millions of years, its star will begin to swell, initiating a process that will ultimately transform this Earth-like paradise into a scorched, uninhabitable world. This presents a haunting and beautiful parallel, a living planet that may be facing its own natural expiration date, a reminder that even the most stable and familiar environments in the cosmos are bound by the finite lives of their stars. 44 light-years from our solar system, a super-Earth named HD 40307G offers a climate that might feel strangely familiar. This world, over 7 times more massive than our own, orbits in the outer reaches of its star's habitable zone, a position that could grant it a true seasonal cycle. Its orbit is slightly elliptical, not a perfect circle, meaning its distance from its Sun changes over the course of a year. This subtle variation would act as a cosmic pacemaker for the seasons, bringing periods of warmth followed by stretches of cooler weather, much like our own winter and summer. The planet's substantial mass suggests a strong gravitational pull, one capable of holding onto a thick, protective atmosphere. This dense air would be essential for moderating temperatures, trapping just enough heat to prevent global glaciation and for creating the pressure needed to keep water liquid on the surface. Picture a landscape of rolling hills and deep valleys where rain clouds gather and rivers flow under the light of a sun very similar to our own. The potential for a diverse environment is profound. With seasons driving changes in weather and temperature, different regions of the planet could develop distinct ecosystems. Lush forests might thrive in the temperate equatorial zones, while colder polar regions could host hardy, tundra-like biomass. The sheer variety of possible habitats makes HD 40307g a world where life would have countless opportunities to take root and evolve into complex forms. Could we one day look upon this distant super-Earth and see a world of vibrant autumn colors, spring blossoms, and summer rains, a testament to the universe's ability to craft environments that echo the comforting rhythms of home? Just 12 light-years away, a world teeters on the edge of possibility. Wolf 1061c is a super-Earth, a rocky giant over 4 times the mass of our own planet, and it orbits so close to its dim red sun that a full year passes in only 18 Earth days. Its location is both a blessing and a curse, placing it squarely within what astronomers call the conservative habitable zone, yet it skirts dangerously close to the inner edge of this region, the boundary where a planet's fate is sealed by the nature of its atmosphere. One path leads toward a temperate world, a place where the planet's substantial gravity could hold onto a thick, protective blanket of air, distributing the star's faint heat efficiently and creating vast, stable pools of liquid water. The other path leads to a hellscape, a runaway greenhouse effect that would transform this promising super-Earth into a twin of Venus. On Venus, a thick atmosphere of carbon dioxide traps solar energy with terrifying efficiency, raising surface temperatures to nearly 900 degrees Fahrenheit, hot enough to melt lead. If Wolf 1061c possesses a similar carbon dioxide-rich atmosphere, it would be locked in a permanent, self-reinforcing cycle of heating, boiling away any oceans and sealing its surface under a crushing, scorching shroud. This is the razor's edge this world walks. Is it a water-rich haven, a testament to the delicate balance that can sustain life, or is it a stark warning of how easily a planet can tip from habitable to hostile? The answer depends entirely on the air it breathes, a secret held tightly by a distant, crimson sun. That delicate balance between a temperate world and a scorching hellscape finds a striking contrast 1,200 light-years away. Kepler-62f presents a vision of profound serenity, a world about 40% larger than Earth orbiting a star cooler and dimmer than our Sun. Its orbit is long and patient, a single year stretching out over 267 Earth days. This distant position within the habitable zone, combined with the star's gentle output, has led scientists to run countless climate simulations to understand its true nature. The results point to a world utterly dominated by water. Kepler-62f is likely a pure water world, a globe completely shrouded by a single, planet-wide ocean dozens of miles deep. There would be no mountains breaking the surface, no continents to interrupt the endless expanse of sea. The entire planet is a single, massive aquatic habitat. The sky above would be a soft, hazy orange, and the only waves would be those driven by the wind across 1,000,000 miles of open water. You might think such a world would be frozen, given its distance from its faint sun, but its thick atmosphere would act as a powerful insulator, trapping just enough heat to maintain a liquid ocean under the clouds. This creates a stable, global environment where the surface temperature might be remarkably similar to Earth's polar seas. The potential for life here is immense. Without land to provide nutrients, life would have to rely on upwelling currents from the deep, bringing minerals and chemical energy from the ocean floor. Imagine entire ecosystems based not on sunlight, but on the geothermal warmth seeping from hydrothermal vents at the bottom of this global abyss. Bioluminescent creatures could illuminate the eternal darkness, creating constellations of living light in the profound depths. Vast forests of algae might drift in the upper layers, and intelligent life could evolve to navigate a three-dimensional world of endless blue, communicating across thousands of miles with low-frequency songs that travel for weeks through the water. Kepler-62f is not a planet of forests and deserts, but a universe contained within a single, breathtaking ocean. The fate of a world can hang on a single, delicate number. HD 85512b is a super-Earth orbiting a star 36 light-years away, positioned precariously at the very inner edge of its sun's habitable zone. This location makes it a world of extremes, where the difference between a temperate paradise and a scorching wasteland comes down to one critical factor: its reflectivity. Astronomers call this the albedo, a measure of how much starlight a planet bounces back into space. A world with a high albedo, covered in bright clouds or ice, reflects a lot of energy, staying cool. A dark world with low albedo, like one covered in vast, black oceans or basalt plains, absorbs that heat and cooks. For HD 85512b, the calculations are stark. If this super-Earth has an albedo similar to Venus, with its brilliant, reflective cloud decks, its surface could be a surprisingly comfortable, balmy world. But if its albedo is lower, more like that of Earth or even Mars, the intense stellar energy it absorbs would trigger a runaway greenhouse effect, boiling its oceans away and transforming it into a permanent, hellish furnace. This places an incredible emphasis on the planet's weather. The presence of extensive cloud cover, especially water vapor clouds, would not just be a meteorological feature, it would be the planet's life support system. Those floating white blankets would act as a global sunshade, deflecting just enough heat to keep the climate stable. So the great question for this world is not merely about water or atmosphere, but about its very complexion. Is it a bright, cloudy jewel or a dark, heat-soaked rock? Its potential for life is written in the skies. A mere 12 light-years from our solar system, the star Tau Ceti shines as one of our closest sun-like neighbors. Orbiting this familiar sun is a world of profound contradiction, Tau Ceti e, a super-Earth whose mass suggests a planet several times heavier than our own. Its location is tantalizing, sitting within the star's habitable zone where liquid water could theoretically exist. Yet this promising position belies a brutal reality. Tau Ceti e orbits so close to its star that its year is shorter than our own, completing a revolution in just 168 days. This proximity bathes the planet in intense stellar radiation, a relentless energy that could have stripped away any youthful atmosphere or triggered a climatic apocalypse. The fate of this world hinges entirely on the nature of its air. One path leads to a super-Venus, a hellish landscape shrouded in a thick, suffocating atmosphere of carbon dioxide. The surface pressure would be crushing, the temperatures hot enough to melt metal, with clouds of sulfuric acid obscuring a bloated, angry sun. The other path, however, offers a sliver of hope. If Tau Ceti e managed to hold onto a thinner, more balanced atmosphere, perhaps rich in nitrogen with moderate levels of greenhouse gases, it could be a super-Earth. In this scenario, its massive gravity would create a stable, protective blanket, potentially giving rise to vast, shallow oceans and continents of a scale we can scarcely comprehend. The intense sunlight would power a vibrant, if alien, biosphere. The evidence tilts this cosmic scale, for the Tau Ceti system is known to be surrounded by a massive debris disk, a belt of asteroids and comets far denser than our own. This suggests a violent, chaotic environment where planetary impacts are common, a history of bombardment that could have either delivered the essential building blocks of life or repeatedly sterilized the surface. Tau Ceti e stands as a stark reminder that location is not everything, a world whose sun-like star offers both a familiar promise and a potentially lethal embrace. The story of GJ 581G is a testament to how science grapples with ambiguity. Announced with great excitement in 2010, This super-Earth was said to orbit squarely in the middle of its star's habitable zone, a perfect position for liquid water. Its mass suggested a rocky world, and its location promised a climate that could be stable for billions of years, but then a shadow of doubt fell. Other research teams, analyzing the same data from the star's subtle wobbles, could not confirm the planet's existence. The signal was faint, buried in stellar noise, and some argued it was merely a statistical ghost. This world became a celestial phantom, both present and absent in our charts. If it is real, GJ 581G is everything we hope to find. Being in the center of the habitable zone is like having a permanent seat in the perfect spot by a campfire, not too close to be burned and not too far to feel the cold. A planet there avoids the razor's edge dilemmas of worlds like Wolf 1061c. It would have the best possible chance to develop and sustain a temperate, Earth-like climate with the potential for vast oceans and continents. The controversy itself reveals a deeper truth about our search. We are pushing our instruments to their absolute limits, straining to detect the faintest whispers of distant worlds. The debate over GJ 581G is not a failure, but a preview of the challenges to come as we hunt for smaller, fainter, and more Earth-like signals. It represents a world of perfect potential, a promise hanging in the balance, reminding us that the most compelling discoveries are often those we must fight the hardest to see. The first confirmed world to truly capture the public's imagination was Kepler-22b. It was the Kepler Space Telescope's inaugural discovery of a planet orbiting squarely within the habitable zone of a Sun-like star, a breakthrough that proved such promising places were not just theoretical. This world is a giant compared to our own, with a radius over twice that of Earth. Its sheer size places it in a mysterious category, leaving its true nature wide open to speculation. It could be a massive rocky super-Earth, a planet with vast continents and deep canyons under a familiar yellow sun, or more likely, it is what scientists call a mini-Neptune, a world with a substantial rocky core but enveloped by a deep, thick atmosphere of hydrogen and helium, a gaseous shroud with no solid surface to walk on. Yet even this possibility holds a tantalizing alternative. If Kepler-22b is a mini-Neptune that migrated from the cold outer reaches of its system inward to the warm habitable zone, its primordial hydrogen atmosphere could have been stripped away by the star's intense radiation. What might remain is an ocean planet, a world with a global sea hundreds of miles deep, capped by a steamy, water-rich atmosphere. Imagine a place where the sky and the ocean blend into one, a perpetual warm fog under the gentle light of a star very much like our own. While its specific conditions remain a mystery, its legacy is crystal clear. Kepler-22b was the pioneer. It transformed the hunt for habitable worlds from a hopeful quest into a tangible reality, proving that the basic ingredients for life are scattered generously across the cosmos, orbiting stars we see with our naked eye every night. But the Proxima Centauri system holds another, colder secret. Orbiting much farther out from the violent red dwarf is a second world, Proxima Centauri c. This planet is a super-Earth or perhaps a mini-Neptune, a frozen giant in the outer darkness of its stellar home. Its year is over 5 times longer than Earth's, a slow, lonely journey around a faint sun that appears in its sky as little more than an exceptionally bright star. The surface of this world, if it has one, would be a frozen wasteland where any atmosphere lies frozen solid on the ground and temperatures plunge to hundreds of degrees below zero. It seems like the last place you would ever look for life, yet this is where one of the most compelling ideas in modern astronomy takes root. What if this frigid planet, like the gas giants in our own solar system, is circled by moons? A large moon orbiting Proxima Centauri c could be warmed not by starlight, but by an internal fire. The immense gravitational pull of the planet would constantly stretch and squeeze the Moon's interior, a process known as tidal heating. This friction generates enormous energy, enough to melt rock and create vast, subsurface oceans of liquid water. We see this in our own celestial backyard. Around Jupiter, the moon Europa hides a global saltwater ocean beneath its icy crust, kept liquid by the relentless gravitational kneading from its giant parent planet. Around Proxima Centauri C, a similar moon could offer a sheltered haven. Its thick, icy shell would protect the ocean beneath from the deadly radiation and flares erupting from the distant star. Life could thrive in that dark, warm sea, huddled around hydrothermal vents on the ocean floor, completely independent of the sun. This transforms our search. We are no longer just looking at planets, but at their moons as well. A frozen, seemingly dead world like Proxima Centauri C could be the guardian of a hidden, liquid oasis, a secret world within a world where life flourishes in the eternal night. Returning to the cosmic archipelago of TRAPPIST-1, we find a world that embodies both the promise and the puzzle of this stellar family. TRAPPIST-1f is the fifth planet from its star, a rocky world slightly smaller than Earth, and it occupies a crucial position within the system's habitable zone. While it receives a bit less stellar energy than its neighbor TRAPPIST-1e, this very fact might be its greatest advantage. Its more distant orbit could allow it to hold onto a thick, robust atmosphere, one that effectively traps the faint red light from its sun. A dense atmosphere would act like a planetary parka, keeping the world warm enough for vast, global oceans to remain liquid. Imagine a world shrouded in a perpetual, deep orange haze, with seas that roll under a gentle, crimson glow. The possibility of liquid water here is strong, but the nature of that water is a mystery. Is TRAPPIST-1f a true water world, a globe completely enveloped by a single ocean, or does it have scattered islands and continents breaking through its saline seas? This is where the true magic of the TRAPPIST-1 system comes into play. We are not just studying one world in isolation. We have 7 planets, all formed from the same primordial material around the same star, yet each occupying a slightly different environment. This is a gift for a field known as comparative planetology. It is like having 7 sibling planets in a single laboratory. By studying their atmospheres side by side, we can begin to understand the fundamental rules of how planets form and evolve. Why does one world retain a thick atmosphere while another loses it to space? What conditions make one planet a desert and another an ocean? If we detect the biosignature of life, say oxygen and methane, in the air of TRAPPIST-1f, but not in the air of its drier neighbor TRAPPIST-1d, that would be a powerful clue. We could start to map the conditions that give rise to living worlds, not with a single data point, but with an entire planetary family charting the path from barren rock to living world. TRAPPIST-1f is more than just a candidate, it is a critical piece in a larger puzzle, a world whose story is inextricably linked to the 6 others sharing its celestial dance. Kepler-442b offers a glimpse of a world in constant flux. This exoplanet, located about 2,540 light-years away, journeys around its star on a path that is far from a perfect circle. Its orbit is distinctly elliptical, a stretched oval that sends the planet on a dramatic yearly pilgrimage between warmth and chill. For part of its year, it swings close to its K-type star, basking in intense heat. Then it travels outward to the far, cold reaches of its orbit. Astronomers place it within the optimistic habitable zone, a region where liquid water could exist for at least a portion of the planetary year. This is not a world of steady, predictable climates, but one of profound seasonal extremes. The shift between these temperature swings would be monumental, far more severe than anything experienced on Earth. Our planet's mild seasons are caused by a slight tilt, but Kepler-443b's entire climate would be governed by its changing distance from the Sun. Life here would face a relentless cycle of boom and bust. Imagine a world where summers are brief, scorching infernos, causing global oceans to steam and vast deserts to expand. As the planet swings away, a long, brutal winter would descend, locking the surface in a deep freeze that could last for many Earth years. How could biology persist through such violent shifts? The answer might lie in dormancy and resilience. Life could retreat underground or into the deep ocean during the extreme phases, entering a state of suspended animation, only to burst forth in the fleeting, temperate periods when the planet is just the right distance from its star. Entire ecosystems might be programmed to bloom, reproduce, and then hibernate in perfect sync with this cosmic rhythm. Forests could grow at a frantic pace during a several-month spring, only to shed their leaves and wait out the long winter as seeds buried safely in the soil. This world challenges our Earth-centric view of stability, suggesting that life may not need a perpetual paradise, but only a recurring, predictable window of opportunity to cling to existence and even thrive. Lytton Star B offers a promise of endurance. This super-Earth, just over 12 light-years away, circles one of the quietest red dwarfs we have ever found. Its star is so stable and flare-free that astronomers have given this world one of the highest habitability ratings of any known exoplanet, a score that reflects its potential to be not just habitable, but comfortably so for eons. While it is likely tidally locked with a permanent dayside and nightside, its substantial mass suggests it could hold onto a thick, Earth-like atmosphere. This dense blanket of air would be the key to its climate, efficiently circulating heat from the scorching sunward side to the frozen dark side, potentially creating a wide, temperate band in the twilight zone where conditions remain stable. The true wonder of Lytton Star B, however, is time. Its stability index indicates this world has probably enjoyed these calm, life-friendly conditions for billions of years, possibly longer than Earth itself. Think of the uninterrupted peace, a planetary environment where the sun never rages and the climate remains constant across millennia. What could life achieve with such a generous timeline? Evolution here would have faced few cosmic catastrophes, allowing for biology to experiment and complexify without being reset by stellar violence. Lush, alien forests could have taken root along that eternal dawn, and intelligent beings might have risen under that constant crimson sky, their civilization enduring for ages we can scarcely comprehend. This world is not a fleeting candidate, it is a potential galactic elder, a testament to the profound possibilities that arise when a planet is given the gift of peace and time. Kepler-1649c is another quiet testament to a cosmic revolution. This world, discovered by the Kepler Space Telescope, is almost exactly Earth's size and mass, a rocky twin orbiting peacefully within its red dwarf star's habitable zone. Its discovery was not an isolated event, but part of a profound pattern revealed by Kepler's tireless gaze. The mission taught us that small, rocky planets are not rare jewels in the cosmos, they are the galaxy's most common output. For every star you see in the night sky, there is a high probability of at least one Earth-sized world orbiting in that gentle, life-giving region where water can flow. This statistical certainty transforms our perspective. The universe is not mostly empty space punctuated by the occasional planet, it is a vibrant tapestry woven with countless potential homes. Kepler-1649b embodies this new reality. It is a member of a vast, silent majority of worlds that share our basic blueprint. The specific conditions here are what elevate it from a statistic to a candidate. Its red dwarf star is older and more settled, offering a stable light source without the violent flares that threaten younger systems. A year on this world is remarkably short, just over 38 Earth days, meaning it orbits snugly and safely within that temperate band. The planet's Earth-like composition suggests it could have a similar internal structure, with a molten core capable of generating a protective magnetic field. This invisible shield would be crucial for deflecting stellar radiation and preserving any atmosphere that might cling to the world, could its surface hold rivers and lakes under a perpetual, crimson twilight. The sheer number of worlds like Kepler-1649c makes the answer feel almost inevitable. We are no longer asking if Earth is unique, but how many of its countless siblings have also learned the trick of life. GJ-1214b presents a world utterly enveloped in vapor. This super-Earth, orbiting a red dwarf just 40 light-years away, is famously shrouded beneath a thick, global atmosphere of steam and hydrogen, an impenetrable veil that hints at a profound secret below. For years, its classification has wavered between a steamy mini-Neptune and a genuine water world, but the most compelling theory suggests a planet with a liquid ocean of staggering depth. This would not be an ocean like our Pacific, but a global abyss hundreds of miles deep, capped by an atmosphere so dense and hot that the very boundary between air and water might blur into a superheated, fluid state. The pressure at the bottom of this sea would be crushing, creating exotic forms of ice not from cold, but from immense force, a hot, solid floor to the aquatic universe. In such a place, utterly cut off from the faint red sun above, how could life possibly gain a foothold? The answer may lie in the planet's own internal fire. On the dark ocean floor, volcanic vents would likely spew mineral-rich, superheated water into the eternal gloom, just as they do on Earth. Around these oases of chemical energy, entire ecosystems could thrive, completely independent of sunlight. Imagine creatures adapted to a world of perpetual pressure and darkness, their forms sculpted by an environment we can barely simulate. They might sense their world through subtle changes in water chemistry or through bioluminescent communication, creating constellations of living light in the profound blackness. The entire planet could be a single, interconnected biosphere, with life drifting on global currents between vent systems separated by thousands of miles. This is a vision of life that rejects our sunny, terrestrial expectations, proving that a living world does not need a friendly surface, or even a surface at all, to burst with possibility. Another Kepler discovery reinforces this staggering cosmic census. Kepler-1648b is a world almost identical in size to our own, a rocky sphere orbiting patiently within its star's habitable zone. Its discovery was not merely the addition of another pin on the galactic map, but a powerful piece of statistical evidence. The Kepler mission was designed to answer one deceptively simple question: what fraction of stars in our galaxy harbor Earth-sized planets in temperate orbits? With the confirmation of worlds like Kepler-1648b, we received a definitive and breathtaking answer: they are everywhere. For every star you see twinkling in the night sky, there is a high probability it hosts a world with a similar size and temperature to Earth. This statistical certainty transforms our entire perspective on the universe. The existence of life is no longer a question of possibility, but of probability. With hundreds of billions of stars in our galaxy, and now knowing that most have at least one such world, the number of potential habitats for life becomes astronomically large. Think of it as a cosmic lottery. We have just learned that the galaxy has printed trillions of tickets. The odds that life holds a winning ticket on only one world, our own, seem vanishingly small. Kepler-1648b is one of those countless tickets. It may not be the most famous exoplanet, but its quiet existence fuels a profound and enduring optimism. We are not searching for a needle in a haystack, we are standing before an endless field of haystacks, knowing that needles are almost certainly hidden within many of them. This fundamental shift, from wondering if we are alone to wondering how many neighbors we have, is perhaps the most important legacy of the Kepler telescope. HD 2-19-134b burns with a stark reminder of our cosmic fragility. This super-Earth, a massive rocky world located just 21 light-years away, is a scorching inferno, orbiting so close to its star that a full year flashes by in only 3 Earth days. Its surface temperature is believed to soar to over 1,200 degrees Fahrenheit, hot enough to melt most metals and turn rock into bubbling lava. It is a world of perpetual incandescent fire, a clear example of a planet that stepped over the line. This line is the inner edge of the habitable zone, a boundary as crucial as it is invisible. The concept of the habitable zone, or the Goldilocks zone, is the single most important idea in our search for life. It defines the narrow orbital band where a planet is neither too close to its star, boiling its water away, nor too far, freezing it solid. HD 2-19-134b is a textbook case of a world that is far too close. It receives a torrent of stellar energy so intense that any atmosphere it might have once had was likely blasted away into space, and any water would have long since evaporated and been broken apart by radiation. This planet is a study in extremes, a place where the conditions for life are not just absent, but violently impossible. Its existence, however, is not a failure. It serves as a critical control in our galactic experiment. By studying worlds like this, we learn to appreciate the delicate balance required for a planet to become a cradle for life. It teaches us that a world can be the right size, the right composition, and even the right age, but if its address is wrong, its potential is forever extinguished. The habitable zone is the universe's ultimate real estate rule, and HD 2-19-134b is a property located squarely in the cosmic furnace. WASP 121b is a place where the very concept of a planet is pushed to its breaking point. This world is an ultra-hot Jupiter, a gas giant orbiting so close to its sun that its atmosphere is literally boiling away into space. The temperatures here are beyond comprehension, reaching a staggering 4,500 degrees Fahrenheit on the dayside, that is hot enough to vaporize iron, titanium, and platinum. Imagine a world where it rains molten iron and the clouds are made of vaporized metal, a celestial forge where the building blocks of planets are torn apart and cast into the stellar wind. The planet is so gravitationally locked and stretched by its star that it has taken on an oblong, football-like shape. Its atmosphere is a maelstrom of violence, with winds screaming at thousands of miles per hour, carrying the evaporated remnants of metals from the permanent day side to the slightly cooler night side. There, the metals might briefly condense into droplets of liquid gemstones before falling back into the inferno. This is not merely an uninhabitable world, it is an anti-habitable world, a graphic demonstration of nature's most destructive forces. WASP 121b serves as a crucial counterpoint to the hopeful, water-rich worlds we have explored. It defines the outer limits of what is possible, showing us the brutal fate that awaits any planet that wanders too close to its sun's fury. Its existence underscores a profound truth about our search, that the habitable zone is not just a region of opportunity, but a razor-thin band of cosmic real estate, a safe harbor nestled between the frozen void on one side and the stellar inferno on the other. Our journey across 30 worlds culminates in a silent, unfolding revolution. The true power of our search lies not just in identifying these distant planets, but in learning to read their very air. The next generation of telescopes is transforming this dream into a tangible science, bringing us to the brink of an answer we have sought for millennia. The James Webb Space Telescope is already leading this charge, its golden eye tuned to the faint chemical signatures imprinted on starlight. As a planet transits its star, a thin sliver of its atmosphere is backlit. Webb analyzes this filtered light, breaking it down into a spectrum, a unique barcode of chemicals. It hunts for the subtle dips in light that betray the presence of water vapor, carbon dioxide, and, most tantalizingly, potential biosignatures. These are gases that, on Earth, are overwhelmingly produced by life. The simultaneous detection of both oxygen and methane in an exoplanet's air would be a seismic event. These gases react quickly with one another, so finding them together suggests a constant, replenishing source, and on our planet, that source is biology. But the search does not end with Webb. On the horizon is an even more ambitious project, the Habitable Worlds Observatory. This proposed space telescope is designed with one primary goal: to directly image Earth-like planets around Sun-like stars and analyze their atmospheres for signs of life. Imagine blocking out the blinding light of a star to see the pale blue dot of a neighboring world, then studying its atmospheric composition from dozens of light years away. This is the next great leap. These instruments will turn the 30 candidate worlds from points of light into rich, complex environments. We will be able to ask if the global ocean of a Hycean world is rich with the chemical waste products of a marine biosphere. We could detect the industrial pollutants of an advanced civilization, or simply confirm a stable, life-sustaining balance of gases on a rocky twin of Earth. The question is no longer if such worlds exist, but which of them are breathing. We are building the tools to listen for that cosmic breath, and the answer is closer than we have ever dared to believe. From molten rock worlds to global oceans under hydrogen skies, these 30 worlds reveal a cosmos far more creative than we ever dreamed. We have found planets locked in eternal twilight, vast water worlds with no land in sight, and super-Earths bathed in the gentle glow of quiet red suns. The sheer variety is a testament to the universe's boundless imagination, proving that the recipe for a habitable world comes in countless forms. This incredible diversity is the most powerful clue in our search. If so many different kinds of planets can exist in that delicate Goldilocks zone, then life itself may be incredibly adaptable, capable of taking root in environments we once considered utterly alien. The silence of the cosmos is not a sign of emptiness, but a canvas of immense possibility. We are living in the golden age of discovery, a time when new worlds are being cataloged almost weekly. Each new telescope, each mission, brings us closer to answering humanity's oldest and most profound question: are we alone? The evidence is mounting that we are not. So the next time you find yourself under a clear night sky, look up at those twinkling points of light. Remember that around so many of them, there are other worlds, other oceans, and perhaps other beings gazing back into the cosmic dark, wondering if they too are alone. Your curiosity is the engine of this exploration. Follow the discoveries, for the greatest chapter in our story is being written right now in the light of distant suns.